Hi, this is Dr. John Bergdorf. In this video, we're going to explore graphing a rational function. And this is one of two videos I have on my channel that give examples of graphing a rational function just so you can see some different behavior depending on the exact nature of the function. Our objective in this video is to graph a rational function defined by an equation consisting of a single simplified fraction, like this one. We're going to sketch the graph of the function defined by f of x equal the polynomial 3x plus 9 divided by the polynomial x squared minus 6x plus 9. There are basically 7 steps that you can go through to get a graph very quickly without plotting a great number of points and with fairly decent accuracy as well. The first step that I recommend is that we locate the y-intercept. Now, the y-intercept of a graph is always found by letting the x value be 0 because a point on the y-axis has an x-coordinate of 0. So I'm going to take my function and substitute zeros wherever I see an x. And you can probably just see you could do this in your head, I'm pretty sure. Plugging in zeros for everything. You'll see that you get 9 over 9, which gives me a y-intercept of 1, and that's not much, but hey, that's the first point. That's a place to start. That's the y-intercept. Now that we have the y-intercept, let's see if we can find the x-intercepts. The x-intercepts are found by factoring the numerator and setting each factor equal to 0. Now in this case, this numerator actually does factor. You could factor out a 3, but the expression is so simple that I think we can just solve for x directly without needing to factor out a common factor. Let's subtract 9 from both sides and then divide by 3, and we find out that the x-intercept is at -3, and we put that right there. So that's 2 points. Let's see what else we can do. Because it's a rational function, there's a very good chance that it will have a vertical asymptote. There are some rational functions that don't have vertical asymptotes, but most of them do. The vertical asymptotes are determined by looking at the denominator, and as it says right here, the recommendation is to factor the denominator and then set each factor equal to 0. Now, we can factor this denominator here by trial and error. It turns out, and if you happen to know about factoring perfect square trinomials, this will be a little bit easier. It factors as x minus 3 times x minus 3. And you can check that out if you like. X minus 3, I wrote it as x minus 3 squared, but that is x minus 3 times x minus 3. And if you use the FOIL rule, you'll get x squared minus 3x plus 9, and that indeed is x squared minus 6x plus 9. So it factors as, in fact, a perfect square. Where the denominators are equal to 0 will give me vertical asymptotes. Because I have one factor repeated twice, there is only going to be one vertical asymptote, and that will be at x equal 3. Actually, I should have done that one little step there. We take each factor and set it equal to 0, and that gives me x equal 3, as you can see. We will say that this asymptote, vertical asymptote, has a multiplicity of 2 because in the denominator, the x minus 3 is squared, so in some sense, the same asymptote happens twice. Okay, that's the vertical asymptote. If we find the vertical asymptote, we should probably also find the horizontal asymptote. Now, horizontal asymptotes are a little bit more complicated to find because there are a number of cases. Depending on the degrees of the polynomials in the numerator and the denominator. The degree of a polynomial is simply the highest exponent on a variable in that polynomial. So, for example, in this case, the polynomial in the denominator has a highest exponent of 2, so we would say that the degree of that polynomial is 2. Whereas in the numerator, there are no exponents on the variable, which means that the highest exponent is really a 1. So the degree of the numerator is 1 and the degree of the denominator is 2. Notice the first case here. If the degree of the numerator is less than the degree of the denominator, which is what's happening here, then the x-axis serves as the horizontal asymptote. So we're going to have the x-axis itself being the horizontal asymptote, and I'm drawing that in like this. Notice that there is a point on the graph on the horizontal asymptote. That can happen. We'll talk about that a little bit later. There are two other scenarios that can happen when you're looking for the horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, what you do basically is create a fraction that consists of the leading coefficient of the numerator divided by the leading coefficient of the denominator. And finally, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And what happens in that case would be worthy of a separate video. So lots of words here, but bottom line, we are in case A, and the horizontal asymptote is simply the x-axis. All right, let's see what we're going to do next. Now we're going to examine the behavior of the graph at the x-intercepts. So as a graph approaches an x-intercept, there's one of two things that can happen. The graph can either pass through the x-axis at that intercept, or it can touch the x-axis at that x-intercept but not cross it and kind of bounce off it. In one case, if you focus very narrowly on right near the x-intercept, it looks kind of like a line. In the other case, it looks kind of like a parabola. If the x-intercept has odd multiplicity, the graph will pass through the axis, like this case. If the x-intercept has even multiplicity, the graph will touch but not cross the x-axis, like this case. So what do we mean by that? I sort of mentioned the word multiplicity before. A multiplicity is determined by basically how many times an x-intercept occurs. And that is determined by whether the polynomial in the numerator is raised to a power of 1, 2, 3, or whatever. In this case, we mentioned before that the denominator is going to have multiplicity 2 because we see the factor of x minus 3 squared. In the numerator, we don't have any squared factors, so this multiplicity is actually like a 1, and that means we are in this case. So we are going to remember that as we approach the x-axis, the graph is going to pass through the axis at that point. And we'll just remember that. And again, looks weird because there's a horizontal asymptote there also. All right. So we look at the behavior of the graph at the x-intercepts, and then we look at the behavior of the graph near the vertical asymptotes. And again, this has to do with multiplicity. If the multiplicity of the vertical asymptote is odd, the branches of the graph near the vertical asymptote will go in opposite directions. What does that mean? Well, let me give you an example of what that would mean. Let's say you have a vertical asymptote right around here. What I mean when I say that the branches go in opposite directions is that on one side of the asymptote, perhaps, the graph will take off towards positive infinity, but on the other side of the asymptote, the graph may take off towards negative infinity. This is what I mean by the branches go in opposite directions. If the multiplicity of the vertical asymptote is even, and that's what I have going on right here, then the branches of the graph near the vertical asymptote will go in the same direction. Now that would be either that both branches take off towards positive infinity, or both branches take off towards negative infinity. Which is which will depend on a more careful look at the graph. But we at least know that in our case, the branches of the graph will go in the same direction. So we'll see what that means. Now we're going to put this all together. We're going to remember, we've got the points that we plotted, and we're going to remember the other facts that we have. We're going to sketch the graph, beginning with the y-intercept if there is one. If you were able to calculate a y-intercept, that is often an excellent point to get you started and may very well be the only point you actually need to know. You may find it necessary to plot one or two other points if you're kind of confused by the shape, and that just means plug in a couple different values of x, but I'm going to suggest that we try not to do that if at all possible. One other note here that is of super big importance: a graph of a rational function will never cross its vertical asymptotes, but it may cross its horizontal asymptote, just not at values of x that are large in absolute value. By large, I mean perhaps 10, 20, 30, either in the positive direction or the negative direction. In other words, we don't have to worry about whether the graph may cross this horizontal asymptote at the x-axis, like way out at positive 700. That's not going to happen. It does, rather obviously though, cross the horizontal asymptote of the x-axis at -3, and we'll have to think about what that means. So the recommendation is that we start by graphing near the y-intercept. And if I look to the left of there, I see that the graph has to come down and hit an x-intercept at -3. So it's probably going to come down kind of shallow like that. But because, and so it will go down below the axis, but because the x-axis is a horizontal asymptote, what will somehow have to happen is that without going too far down, the graph is going to have to sneak back up and basically approach that x-intercept, or excuse me, that horizontal asymptote without touching or crossing it. So something like that, roughly speaking. Now, as you go from the y-intercept to the right, you see that there is a vertical asymptote, and your thoughts may be, okay, well, does the graph go up towards infinity at that asymptote, or does it go down? There's always some way that you can eliminate one of the two options. And the way to eliminate the fact that it is not going to go down is if this branch went down towards positive infinity, the graph would have to cross the x-axis somewhere between 0 and 3, and we've already determined there's no x-intercept there. So the only way this graph can go is if it continues up like this and in some nature approaches that vertical asymptote going towards positive infinity. What about on the other side of the vertical asymptote? We don't have any points plotted over there. And this may be a point where if you feel like you're not confident, you might plug a value of x that's like 4 or 5. But I really don't think you need to. We do know that the branches of the graph, as we approach this vertical asymptote, are going in the same direction, both approaching positive infinity. So this branch is going to be doing like the branch on the left, coming down, approaching the horizontal asymptote, never crossing it because we have discovered that there is no x-intercept off towards the right of this graph. So it's going to come down and approach something like that. That is a rough sketch of the graph. Ideally, it'd be nice if it weren't quite so lumpy right around in here, but I think I've done a fairly decent job of getting what the graph will look like. Quick, easy, quick sketch. If you're not looking for a tremendous accuracy, but a general idea, that should do it. But in conclusion, what I decided I would do is graph the same function using Desmos, which is a program that does graphing that's free and available on the internet. And let's kind of see if we see the same things. This graph really does look about the same. I think we can imagine that there is a vertical asymptote at x equal 3. Sure does look like the x-axis is a horizontal asymptote. Notice right here that the graph does cross the x-axis and go down below it a bit, but it gradually sneaks back up towards the x-axis as an asymptote. And so if I look back to my hand sketch, it's pretty close, just a little bit more elegant. So I hope that's a useful example of how you can graph a rational function. There is a second video that gives a different example, and so I hope you'll find those helpful and that you'll find them fun.